Hi everyone, I am Mary Swarna Latha, working as an assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss the probability distribution function, the probability density function, and the corresponding properties. So first, we are seeing the probability distribution function. In the previous lectures, already we have seen the definition of random variable and how the events have been defined on the random variable x. Today, we are going to see the definition of probability distribution function. The probability distribution function can be defined as, it is defined as the probability of the event. What is the event here? X is less than or equals to x. That is called as the probability distribution function. The probability distribution function is denoted by the capital letter F and the distribution function of the random variable x. Therefore, here I am writing the random variable x and here x, small x. So, the distribution function of the random variable x can be denoted by capital F suffix x of x is equals to the probability of the event. What is the event here? X is less than or equals to x. So, that is the definition of the probability distribution function. And already we have seen the classification of random variables. The random variables are classified into two types. They are continuous random variables and discrete random variables. So the continuous random variables, the distribution function is also continuous, whereas the distribution function for discrete random variable is a staircase waveform. The probability distribution function for discrete random variable is a staircase type and the probability distribution function for a continuous random variable is also continuous. So let us see the graphs, how the graphs of the distribution function for a discrete random variable as well as for continuous random variable. The first figure shows the distribution function of a continuous, a discrete random variable. So if you observe the figure shape is like staircase. And if you observe the second figure represents the distribution function of a continuous random variable. So if you observe the second figure, the distribution function is also continuous for a continuous random variable. And the distribution function for discrete random variable is like a staircase waveform. So we have seen the definition of the probability distribution function. Once again, we'll revise that. The probability distribution function is defined as, it is the probability of the event x is less than or equals to x. So let us see the properties of the probability distribution function. The first property is 0 less than or equals to fx of x less than or equals to 1. So what does it mean? Always the probability distribution function lies from 0 to 1. That is, the minimum value is 0 and the maximum value is 1. So how can you prove this property? So what is the probability distribution function? Fx of x is equals to p of x is less than or equals to x. It's nothing but, let us say, I am denoting a is equals to the event x less than or equals to x is equals to a. Now, already we have seen the axioms of the probability. What is the first axiom? Says that the probability of any event always from 0 to 1. So, the distribution function is also probability of an event only. That's why the distribution function always lies from 0 to 1. The minimum value is 0 and the maximum value is 1. This is the first property of the distribution function. So let us go for the second property. So what is the second property? States that fx of minus infinity is equals to 0 and fx of infinity is equals to 1. So let us see the first one. What is the first one? The distribution function at the value x equals to minus infinity is equals to 0. Now we know that what is the distribution function fx of x is equals to p of x is less than or equals to x. Now, what is the first value? We are taking the distribution function at x equals to minus infinity. Therefore, what is my x here? Minus infinity. That is nothing but what? P of x is less than minus infinity plus p of x equals to minus infinity. So we don't have any values less than minus infinity. So this is an impossible event. The probability of the impossible event is 0. Therefore, this is nothing but 0. And the random variable cannot be equals, the value of the random variable cannot be is equals to minus infinity. Therefore, the p of x equals to minus infinity is equals to 0. Therefore, the distribution function for the value x equals to minus infinity is equals to 0. It means fx of minus infinity is equals to 0. And second one is what? The probability distribution function at the value infinity is equals to 1. That we have to prove now. Now, we know the definition of the distribution function. So it states that the probability of the event x is less than or equals to x. Now, p of x is less than or equals to. We want to calculate the distribution function at x equals to infinity. Therefore, take the x value, small x value as infinity. So, it's nothing but what? P of x less than or equals to infinity. So, P of x less than or equals to infinity is nothing but P of s only, because all the random variables definitely will be less than or equals to infinity. It means it is including all the values of the experiment. That's why the event x less than or equals to infinity is nothing but the sample space, which we have already discussed in the previous lecture. Therefore, what is the probability of the sample space is equals to 1. That's why we can define the probability distribution function at x equals to minus infinity is equals to 0 and at x equals to infinity is equals to 1. This is your second property. And the third property states that the distribution function is an increasing function of x, or else we can define it as the distribution function is always a non-decreasing function of x. What does it mean? Fx of x1 is less than or equals to fx of x2 if x1 less than x2. In order to prove this or in order to verify this, I am taking an example. So this is a random variable x. It is taking the values from 1 to 4. And the corresponding probabilities of the random variables are given by 1 by 4, 1 by 8, 1 by 2 and 1 by 4 for the corresponding values 1, 2, 3, 4. Now, so we will calculate first fx of 1. So what is my fx of 1? Nothing but p of x is less than or equals to 1. So p of x is less than or equals to 1 means how many values are having only at x equals to 1. We don't have less than 1 because my x is defining only from 1. Therefore, it's nothing but p of x equals to 1. So what is p of x equals to 1 from the distribution table? At x equals to 1, the probability is defined as here 1 by 4. Therefore, what is my fx of 1 is equals to 1 by 4. Let us calculate the distribution function at x equals to 2. That is nothing but fx of 2. So, what is my fx of 2? X is less than or equals to. Here, what is my small x? In place of small x, I am having 2. Therefore, p of x is less than or equals to 2. Now, x is less than or equals to 2 means up to here you have to take. You are having only 1 and 2. Therefore, that is nothing but p of x equals to 1 plus p of x equals to 2. So, the probability x less than or equals to 2 is nothing but p of x equals to 1 plus p of x equals to 2. So, you have to take up to the value of 2. So, you are having only 2. Then, what is p of x equals to 1? What is the probability? That is nothing but here 1 by 4 plus at x equals to 2, the probability is 1 by 8. So, 1 by 8. So, 1 by 4 plus 1 by 8. So, if you take the LCM, then you are going to obtain. So, 2 plus here 1, that equals to 3 by 8. So what is the probability of the event p of x less than or equals to, that is nothing but what? Fx of 2. What is my fx of 2? I got p of x equals to 1 plus p of x equals to 2. That equals to what I made here? 3 by 8. Now, if you observe the values of fx of 1 and fx of 2. So, here the fx of 1 is less than fx of 2. That is, what is my fx of 1 here? 1 by 4. So, 1 by 4 is less than 3 by 8. It means the distribution function is always an increasing function of x. So here what is x1? Here my x1 is 1 and what is my x2 here? 2. So x1 is if x1 is less than x2. So 1 is less than 2. It means fx of 1 is less than fx of 2. Now one more thing here given equal to also. Let us see for what cases you are going to get fx of x1 is equals to fx of x2. So let us calculate fx of 4. So what is fx of 4? P of x is less than or equals to 4. It means I have to take the probabilities up to 4. Up to 4 means P of x equals to 1 plus P of x equals to 2 plus P of x equals to 3 plus P of x equals to 1 by 8. So if I add, so I'll get 1 by 4 plus 1 by 8 plus 1 by 2 plus 1 by 8. So if I take the LCM, then so 2 plus here 1 plus 4 plus 1. So that equals to 8 by 8. That equals to 1. Now what is my fx of 4? That is equals to 1. Let us calculate fx of 5. So what is fx of 5? That is nothing but p of x is less than or equals to 5. That is nothing but I had to add the probabilities up to 5. So up to 5 you are having only up to 4 only. Nothing but what? P of x equals to 1 plus P of x equals to 2 plus P of x equals to 3 plus P of x equals to 4 plus P of x equals to 5. Now, what is P of x equals to 1? 1 by 4 plus P of x equals to 2 is 1 by 8 plus 1 by 2 plus 1 by 8 plus and P of x equals to 5. I don't have. Therefore, it is impossible event. The probability of the impossible event is 0. Then what is my fx of 5 is equals to 1. So if you observe here, fx of 4 is equals to fx of 5. If you observe, fx of 4 is equals to fx of 5. And here what is my x1? Is less than x2. It means always the distribution function is an increasing function of x. That is nothing but fx of x1 is less than fx of x2 or it may be fx of x1 is equals to fx of x2. For what condition? If x1 is less than x2. In this example, what you have observed? Here my x1 is 1 and x2 is 2. So fx of 1 is less than fx of 2. And the second case, what you have taken, because I have given equal to also. The first case I have taken fx of x1 is less than fx of x2. And second case, what I have taken, I have considered for what cases I am going to get fx of x1 is equals to fx of x2. For that, I have taken two values. X1 I have taken as 4 and x2 I have taken as 5. And I have calculated the corresponding distribution functions fx of 4 and fx of 5. If I observe this, both the values at x1 equals to 4 and x2 equals to 5, both these are equal. So even though x1 is less than x2, in this case I am going to get fx of x1 is equals to fx of x2. So therefore the distribution function is always a increasing function of x, or else it is also called as non-increasing function of x. So this is your third property of the distribution function. And coming to the fourth property. What is the fourth property of the distribution function? States that the probability of a random variable x between two values, that is nothing but x1 and x2, is equal to the difference of the distribution function of the corresponding values. It means P of x1 less than x less than equals to x2 is equals to fx of x2 minus fx of x1. Let us prove this property. In order to prove this property, I am taking two events. The first event is A is equals to X is less than or equals to X1. That is the first event I am considering. One more event I am considering as B. So that is equals to X1 less than X less than or equals to X2. I am considering two events. The first event is X is less than or equals to X1 and second one is the random variable X takes from X1 to X2. If you observe this, then what is my A union B? That is nothing but what? X is less than or equals to X1 union X1 less than X less than or equals to X2. Now what is A union B? X is less than or equals to X1 and X is from X1 to X2. Then what is my A union B is equals to? That is nothing but X less than or equals to X2. So let us see by taking a graph. So this is my random variable X and is having two values up to X1 and this is up to X2. What I want to calculate the probability between 2 points, that is from X1 to X2. In order to prove this property, what I am considering that? I am considering two events. What is my first event is X is less than or equals to X1. This is my first event. And what is my second event? X1 less than X less than or equals to X2. In this here, X value is up to X1. And here up to X2 is nothing but what? X1 to X2. I am considering two events. And what is the union of these two events? It's nothing but what? What is union of X1? So X less than equals to X1 and X is from X1 to X2. That is nothing but it is taking up to the value of X2. That is nothing but X is less than equals to X2. Therefore, what is my A union B is equals to X is less than equals to X2. So let us calculate. And what is the A intersection B? What is my A up to X1? And what is my B from X1 to X2? Do these two events are having any common elements? No. Therefore, what is A intersection B is equals to pi. Now let us go for the probability union property. What is that property? P of A union B is equals to what? P of A plus P of B minus P of A intersection B. Now, P of A union B. So, what is my A union B? Nothing but here X is less than or equals to X1. That is nothing but here X is less than or equals to X2 only. Directly I am writing here that equals to P of A. So, what is my A here? X is less than or equals to X1 plus P of B. What is my event B here? From X1 to X2. This is my event A and this is my event B. So, this is my event A union B. Now, what is my P of B equals to? X1 less than X less than equals to X2 minus P of A intersection B. So, these two events does not have any common elements. Then, what is A intersection B equals to pi? So, P of pi. So, what is from the definition of the distribution function? So, what is the definition of the distribution function? Fx of x is equals to P of x is less than or equals to x. So, this is the definition of the distribution function. Now, in place of x, I am having here x2. Then, how can I represent this as fx of x2? So, fx of x2 is equals to what? P of x less than or equals to x1. So, now in place of x, here I am having x1. Then, I can replace this x by x1 here. That is nothing but what? Here, fx of x1 plus P of x1 less than x less than or equals to x2. And what is the probability of null event? It is 0. So, from this, so what is the probability that the random variable takes the values from x1 to x2 is equals to fx of x2 minus fx of x1. So, this is a probability of the random variable x takes from x1 to x2 is equals to what? It is a difference of the distribution function of the corresponding values. This is your fourth property of distribution function. So, let us go for fifth property. So, what is the fifth property? States that the probability of the event x greater than x is equals to what? 1 minus fx of x. So, how can you write x greater than x as? You can write this as what? Nothing but what? Here, the sample space minus x is less than equals to x. Now, what is the probability that x greater than x is equals to p of s minus p of x is less than equals to x. So, what is my p of s? Here, s is nothing but the sample space. P of s is equals to 1. So, 1 minus p of x less than equals to x, that is nothing but fx of x. Therefore, the probability of the random variable x takes any number greater than x is equals to 1 minus fx of x. This is your fifth property. And coming to the sixth property, the sixth property states that always the distribution function starts from the right. It means, for example, I am considering a distribution function x, and this is the distribution function in y-axis. Then let us consider this is my distribution function. Let us consider this is a value at x equals to 0, and this is a value at x equals to 1, this is a value at x equals to 2, and this is a value at x equals to 3, and so on. So, and let us consider the value at x equals to 1 is 1 by 3, and the value at x equals to 2 is, let us say this is 2 by 3, and let us say the value at x equals to 3 is 3 by 3, let us say. So, it is then, if you take, for example, I am taking the value at x equals to 2. At x equals to 2, what is my distribution function? I am having here two values. What are the two values? One is 2 by 3, and the other value is 3 by 3. Which value I have to consider? Always I have to consider the value from the right. So, for 2, what is my right value? 3 by 3. It means always the distribution function starts from the right. You should not consider the left value, you have to consider only the right value. This is your sixth property of the distribution function. So, therefore, these are the properties of the probability distribution function. So, we have seen the distribution function formula and then definition. After that, we have seen the properties. So, let us see that the probability distribution function for a discrete random variable. So, for a discrete random variable, you can define the probability distribution function as fx of x is equals to sigma I equals to 1 to n p of x equals to xi into u of x minus xi. Here, u of x minus xi is nothing but it is a delayed unit step function. How can you define the delayed unit step function? What is u of x? So, this is a unit step function. How it is defined? So, this value is 1 when x is greater than equals to 0 and 0 when x less than 0. So, if you observe here, this is my x and this is my u of x. So, for x less than 0 it is 0, and when x is greater than equals to 0 it is 1. This is my u of x. Then, what is the delayed unit step function? Nothing but it is delayed by how many units? By units of xi. So, how can you define u of x minus xi? This is equals to 1 when x is less than equals to xi and 0 for when x less than xi. So, when x is less than xi, it is 0, and when x is greater than equals to xi, the value is equals to 1. So, this is my unit step function. So, you can write down the distribution function for a discrete random variable as the sum of the is equals to the what? The sum of the unit step functions, the delayed unit step function, and whose amplitude has been multiplied by the corresponding probabilities. So, this is a distribution function for a discrete random variable. The same thing if you plot on the graph, you'll get a staircase waveform. So, let us take one example. So, what is my example here? Consider the experiment of tossing 4 coins. The random variable x associated with the number of tails showing up. Compute and sketch the CDF of x. So, what is the experiment they have given? That tossing 4 coins. So, when you toss a coin for 1 coin, the sample space is only 2, you will get only head or tail. So if you toss 4 coins, then what is the sample space? How many possible elements you are going to get? You are going to get 16 possible elements. Okay. And the random variable x is associated with the number of tails. And what is my random variable here? X is equals to here. X is equals to number of tails. This is my random variable. What I have to do here? I have to compute and then sketch the distribution function of x. So when I toss a coin 4 times or when I toss 4 coins, what is the list of all the possible outcomes? So first coin I may get head, second coin head, third coin head and fourth coin also head. This is the first possibility. And next possibility it may be first 3 times head and the fourth coin is tail. And next possibility is first 2 coins head, third coin tail and fourth coin is head. So like that. So this sample space lists all the possible outcomes. How many elements are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the list of all the possible outcomes. Okay. Now what I have to do here? I have to calculate the distribution function as well as I have to sketch the distribution function of the random variable x. Now what is my x here? X represents the number of tails. So how many x it is taking? X values, can you tell me? So nothing but if I get 0 number of tails, I may get only 1 tail, or I may get 2 tails, or I may get 3 tails, or I may get 4 coins heads also. What is my first value here? Number of tails here. First is nothing but 0. 0 nothing but no tails. So when I toss the 4 coins, so all that coins shows the tail heads only. It means that number of tails are 0. And second one is taking x value is taking 1. Then nothing but only 1 coin is showing tail and the remaining coin are showing the heads. So like that the possibility is up to 4. 4 is nothing but all the 4 coins shows the tail when the coins are tossed. So this is my x. It is taken from 0, 1, 2, 3, 4. Let us see. So when I get x equals to 0, I'll get x equals to 0 when all the 4 coins shows heads only. When I'll get x equals to 0 when all the coins getting as heads only. Because my x is nothing but number of tails. No coin is showing the tail. It means the coins are not showing tail, nothing but they are showing the head. So now the sample space, how many possibilities are there? Only 1 possibility is there. Therefore, for x equals to 0, what is the possibility here? All the coins are heads. Then what is p of x equals to 0? So totally I am having 16 elements. So out of 16, only 1 possibility is there. Then what is the probability? Is equals to 1 by 16. Because when I toss it once, the sample space consists of 2. If I toss the coin for 2 times, or if I toss 2 coins, then the sample space consists of 2 square, nothing but 4 elements. If I toss the coin for 4 times, or if I toss 4 coins, the sample space consists of 2 power 4, nothing but what? 16. So total it consists of 16 number of elements. And second value, what is the x value is taken from 0, 1, 2, 3, 4. Let us see for what possibilities I am getting x equals to 1. So when I get x equals to 1, the first 3 coins heads and the fourth coin is tail. Or else for the first 2 coins is heads, only the third coin is tails. And third possibility is second coin tail and the fourth possibility is the first coin tail. How many possibilities here? 1, 2, 3, 4. So out of 16 possibilities, my favorable outcomes are 4. Therefore, what is my p of x equals to 1 is nothing but 1 by 16. This is 1 by 16, 1 by 16 plus 1 by 16, nothing but 4 by 16. So what is my 4 by 16 value? Nothing but 1 by 4. Similarly, I can calculate the probability for x equals to 2. X equals to 2 is nothing but the probability that the number of heads are 2. So let us say, so these are the possibilities. I'm getting the number of heads are 2. Here 2 heads, 2 heads, 2 heads. How many possibilities variable outcomes here? 1, 2, 3, 4, 5, 6. So what is my probability? Number of variable outcomes by total number of possible outcomes are 16. So 6 by 16 that equals to 3 by 8. And next one is probability that the number of tails are equals to 3. So in what cases I'm going to get 3 tails? So 1, 2, 3, 4. 4 cases. So 4 by 16 that is nothing but 1 by 4. And the last value is P of x equals to 4. P of x equals to 4 is nothing but the probability that the number of tails are equals to 4. That means all the 4 coins are showing tails only. There is only one possibility out of 16 possibilities. Then what is P of x equals to 4? That equals to 1 by 16. Now I have calculated all the probabilities. Next, what I have to calculate? I have to calculate the distribution function. Now, what is fx of 0? So, fx of 0 is nothing but fx of 0. That is nothing but P of x is less than or equals to 0. So, you don't have less than or equals to 0 because my x is taken from 0 to 4 only. Therefore, P of x equals to 0. What is P of x equals to 0? That equals to 1 by 16. Next, fx of 1. So, what is fx of 1? Then nothing but P of x less than or equals to 1. So, less than or equals to 1 means up to 1 you have to take. You have to take 0 and 1. So, there is nothing but P of x equals to, so P of x equals to 0 plus P of x equals to 1. That is nothing but 1 by 16 for P of x equals to 0 and 4 by 16 for P of x equals to 2. So, x equals to 1. Then nothing but 5 by 16. Similarly, you can calculate fx of 2 and fx of 3 and fx of 4. So, if I calculate what is fx of 0, 1 by 16, fx of 1 is 5 by 16, fx of 2 is 11 by 16, and fx of 3 is 15 by 16, and fx of 4 is 1. And what about fx of 5 is also 1, fx of 6 is 1 up to fx of infinity is equals to 1. So, the same thing I'm plotting in the graph. So, the x-axis I'm taking x, and the y-axis I'm taking the distribution function fx of x. What is my x is ranging from number of tails? Nothing but when I toss 4 coins, so the total possibility is from where to where? Number of tails are from 0 to number of tails are 4. That is nothing but 0 to 4. That is what is my x here? 0 to 4. And these are and the y-axis I'm showing the corresponding distribution functions. They are 1 by 16, 5 by 16. At x equals to 0, it is 1 by 16. At x equals to 1, it is 5 by 16. At x equals to 2, it is 1 by 16. At x equals to 3, 15 by 16. At 4, it is 1. At 5, it is 1. And so on. At x equals to infinity is also 1. And already we have seen that the distribution function for a discrete random variable is a staircase waveform. Therefore, this is the distribution function. How do you plot for the given random variable? Let us take one more example. This is a distribution function for a continuous random variable. So, they have defined the distribution function. What you have to do, you have to plot the graph of the distribution function as well as you have to calculate the probability that x is greater than 1 by 4. Now, what is fx of x equals to, they have given 0 when x less than 0. When x is 0 to 2 by 3, the value is x plus 1 by 3. And x is greater than 2 by 3, the value is 1. This is the distribution function they have defined. Now, you have to plot this. So, when x is less than 0, what is my distribution function? 0. Next, when x is 0 to 2 by 3. Now, what is x is from 0 to 2 by 3. So, first I am taking x equals to 1 by 3. When x is 1 by 3, what is fx of x equals to? So, 1 by 3, nothing but what? 1 by 3 plus 1 by 3. That equals to what? 2 by 3. So, therefore, at x equals to 1 by 3, what is the value here? 2 by 3. Next, when x is greater than 2 by 3, x equals to 2 by 3. Means I am taking here fx of 2 by 3. So, fx of 2 by 3 means, what is my x value here? 2 by 3 plus 1 by 3. Then equals to what? 1. So, what is at x equals to 2 by 3, the distribution function is 1. And they have given when x is greater than 2 by 3, it is 1. So when x is greater than 2 by 3, so what is my fx of x equals to 1? So like that, I can plot the distribution function. If you observe the distribution function of this random variable x, what type of random variable here it is? Continuous random variable. Therefore, for a continuous random variable, the distribution function is also continuous. And the second thing you have to calculate the probability that x is taking greater than 1 by 4. That probability I have to calculate. So, p of x greater than equals 1 by 4, nothing but 1 minus fx of x. This all we have seen from the properties of the distribution function. So, when x is less than equals 1 by 4, it means, what is my x here? It is in this range. So, when x is in this range, what is fx of x equals to x plus 1 by 3. Now, what is my x here? 1 by 4 plus 1 by 3, that equals to what? 5 by 12. So, like that, I can calculate the probability of the events from the given distribution function. So, this I am using the fifth property of distribution function. So, we have seen the distribution function properties. Let us go for the probability density function. So, how can you define the probability density function? That can be defined as the differentiation of the distribution function gives the density function here the small fx of x. Always the density function has been represented by small f and the suffix x. X is nothing but for the random variable x and bracket small x. So the density function of random variable x is defined as the differentiation of, here what is capital fx of x, that is called as the distribution function. So the differentiation of the distribution function gives the density function. Now, for a discrete random variable, let us write the density function. So, already we have for discrete random variable, we have written the distribution function. So, here you got here u of x minus xi. Now, how do you get the density function? The differentiation of the distribution function. So, what is the differentiation of the unit step function? The differentiation of unit step function gives the impulse function. Therefore, for a discrete random variable, the density function fx of x can be written as sigma equals to 1 to n p of xi into del of x minus xi. Here, what is del of x minus xi is called as the unit impulse function. How it is defined? Del of x is equals to 1 at x equals to 0 and 0 for when x is not equals to 0. Similarly, how can I define del of x minus xi is equals to 1 for x equals to xi and 0 for x is not equals to xi. In place of horizon, I am going to get xi. So, this is a density function for a discrete random variable. So, let us see the properties of the probability density function. So, what is the first property? Says that the distribution function is always a non-negative number. The distribution function is always a non-negative function or non-negative number. That is the first property. And the second property states that integration minus infinity fx of x dx is equals to 1. What does it mean? The area under the density function is always unity. The area, how do you calculate the area? Integration of any the function. So you'll get from the limits minus infinity, you are going to get the area. So it is the area of what? The density function. So the area under the density function is equals to 1. So this is your second property. How do you prove this property? So what is fx of x is equals to the differentiation of the distribution function. Now, so what is the integration minus infinity? What is my fx of x? D fx of x by dx into dx. So, I am taking the LHS first. So, when integrating and differentiating, both will be cancelled. Then, what I am going to apply here? Fx of x. And what are the limits here? Minus infinity and infinity. That equals to fx of infinity minus fx of minus infinity. So, from the properties of the distribution function, what is fx of infinity value? It is 1. And fx of minus infinity value is 0. That equals to what? 1. It means the area under the density function is equals to 1. It means integration minus into infinity fx of x dx is equals to 1. It is important property in order to check that whether the given density function is valid or not by derivating this density function over the limits minus into infinity. If you get that is equals to 1, you can say that it is a valid density function, or else it is not a valid density function. And third property of density function states that the distribution function fx of x can be calculated in terms of density function by integrating the density function over the limits minus infinity to x. That is, fx of x is equals to integration minus infinity to x fx of x dx. Here this represents the density function, small f, and capital F represents the distribution function. It means if you know the density function, you can calculate the distribution function. Now, how do you prove this property is, so integration minus infinity to x. How can you define the density function? Now, from the definition of density function, so it is defined as the derivation of the distribution function. So, dx. What is my density function? Then nothing but the differentiation of the distribution function, capital F. I am taking the RHS first. Next, when I integrating and differentiating the respect to x, both will be get cancelled. Then I am going to get here fx of x, and what are the limits here? I am going to get here minus infinity and x. The lower limit is minus infinity and the upper limit is x. And equals to what? Fx of x minus fx of minus infinity. And equals to fx of x minus, from the properties of distribution function, fx of minus infinity is equals to 0. That equals to what? Fx of x, that is nothing but LHS. It means you can write down the distribution function in terms of the density function. How can you obtain? By integrating the density function over the limits minus infinity and x, you are going to obtain the distribution function. That is your third property of the density function. And the fourth property states that the probability of a random variable x between two values a and b is equals to, how can you obtain here? By integrating the density function over the limits a comma b. So let us prove this property. It means if you want to calculate the probability in terms of density function, what you have to do? You have to integrate the density function over the given limits. So let us go for the first one is, I am taking the RHS. What is my RHS here? Sorry, LHS. Integration a to b fx of x dx. Now, so integration a to b. From the definition of density function, it can be defined as the derivative of the differentiation of the distribution function gives the density function. Then, what I am going to apply here? Here, the integration and the differentiation will get cancelled. Both are with respect to x. Then, what I am going to obtain here? Fx of x. And what are the limits here? A to b. So, the limits are a to b. And equals to, substitute the upper and lower limits. I am going to obtain here fx of b minus fx of a. Now, from the properties of the distribution function, what can you write down? Fx of b minus fx of a. That is equals to the probability of the event x from a to b. Therefore, if you want to calculate the probability of a random variable takes from two values, but a to b, then you can calculate in terms of density function as by by integrating the density function over the limits a comma b, you are going to obtain the probability between two values. In terms of density function, this is a formula to calculate the probability between two values. So, I am taking one example here. In a cost price shop, the amount of rice they are defined in terms of hundreds of kilos that sells in a day is a random variable, and they have given the density function of the random variable fx of x equals to cx when x is from 0 to 3 and c into 5 minus x when x is 3 to 5 and equals to 0 otherwise. So, what is x they have given? X is nothing but the amount of rice that sells in a day. So, amount of rice in kilos that cell in a day. That is my x here. So for that x they have given the density function. What you have to calculate, for what value of c fx of x is valid. And second problem is, what is the probability that the number of kilos of rice that will be sold? First one is more than 200 kilos and second one is between 150 and 400 kilos. Okay. So they have given the density function. You have to calculate C value. So what they have given that? They have given that it is a valid density function. So for a valid density function, so what is the property? Then nothing but you have to use the second property of the density function. The area under the density function is equals to 1. So you have to use the property 2 of the density function. And they have given the density function from where to where? 0 to 3 it is Cx. So I am writing this as 0 to 3 Cx dx plus when x is 3 to 5 it is C into 5 minus x. So when x is 3 to 5, this is my density function, C into 5 minus x. So C into 5 minus x dx that equals to 1. Now integrate and then calculate. You are going to get C is equals to 2 by 13. If you simplify, you are going to get C equals to 2 by 13. So just simplify and then calculate the value of C. You are going to obtain as C equals to 2 by 13. And what is the second problem they have given? Find the probability that the number of kilos of rice that will be sold more than 200 kilos. It means this is your second bit. P of what is my x here? I define the x as amount of rice in kilos. How many kilos they have given? They have given that more than 200 kilos. So more than 200 kilos is nothing but you have to take x is greater than 2 because they have given already x in kilos. That's why it should not take here 200. You have to take p of x is greater than 2. So p of x is greater than 2 means from where to where you have taken the maximum is up to 5. So you have to take from p of x equals to 2 to and the maximum actually 2 to x is greater than 2 nothing but 2 to infinity. But my maximum value of x is defined only up to 5. That's why I am taking from 2 to 5. So in 2 to 5, what is my the density function? C into 5 minus x. Okay. So C into 5 minus x dx. Don't make equal to 1 because you have to calculate this value. What is C value you got? 2 by 13 into 5 minus dx. So this gives a probability that there are rice sold more than 200 kilos in per day. And what is the next problem? We have to calculate the probability that 150 to 400 kilos. 150 kilos to 400 kilos. So you simplify this, you can get the probability. And next problem is what? You have to calculate the amount of rice sold 150 kilos and 400 kilos. It means 1.5 because already I have defined x in terms of kilos. That's why don't write here 150, write down 1.5. So 1.5 to 2. So 1.52 means you have to use which property? Property 4 of density function. It means from 1.5 to 4. So when x is 1.5 to 4, it means this is this range 0 to 3. Okay. Then this range, what is my density function? C into x. Write down here C into x dx. Now what is my C here? 1.5 to 4. 2 by 13 into x into dx. So if you simplify this, then you are going to get the probability of the amount of rice that will be sold from 1.5 to 200 kilos. So like that, you can calculate the probability of any event using the density function by using the fourth property, and you can state that whether the given density function is valid or not by using the second property of the density function. So in this lecture, we have discussed the definition of the distribution function, density function, as well as we have seen the properties of distribution and density function. Along with that, we have discussed some examples. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.